Well, thank you all very much for coming. I would like to start off with a tiny bit of context for the research that I completed. So this is a picture of California, and you can see a whole bunch of agriculture, an ocean. This is the ocean, and the agriculture is about 200 meters. And so this is in the Salinas Valley, and there's about $10 billion worth of agriculture coming out of here every year. And because they're so close to the ocean, a lot of the groundwater that is used for the irrigation comes from the ground, they suck it out, and that has problems with sort of seawater intrusion. And so there is a lot of interest in sort of the management of the groundwater practices. And one of the techniques to do that is called managed aquifer recharge. And this up here is a managed aquifer recharge pond. And so California gets a lot of rain actually in the winter, all sort of at once. And so that comes in, and so you want to capture that, put that in a pond, have that infiltrate down, and then in the summer, recover that water. And so the scientific questions here are, where does that water go? And sort of how does it move in the subsurface? And so that's an interdisciplinary question that brings together geology, hydrogeology, and if you want to image where that water goes, also geophysics. And so this was a study that I was involved in my undergrad, where we used a geophysical method to image where that water was going. What was sort of interesting about this study was it was a new geophysical probe that we created to actually get a lot of estimates, both spatially and temporally, of the hydro side of things. So this brings together the disciplines of hydrogeology, geophysics, and geology. And again, that's the fluid flow side of things, actually imaging it and knowing something about the subsurface. And so under the hood of all of these disciplines are a lot of simulation tools and methods. And so for saturated hydraulic, you have Darcy's equation for the vadose zone, which is that region between the ground surface and the water table. We have Richard's equation, which describes that. In geophysics, there's a whole host of methods: direct current resistivity, electromagnetic methods, magnetotellurics, potential fields, gravity and magnetics. And in geology, there's the interpretation of these in sort of a sensible way, as well as the interpolation of data under the surface. And so all of these disciplines have different types of data that they're collecting. And those data are used to inform all sorts of models of the subsurface. And so it's good to collect these different data sets because the models tell you something different about the subsurface. And so the data are sensitive to either different physical properties or different sensitivities of those physical properties. And so sort of what is the sensible thing to do, and sort of the state of the science. And so there's a whole bunch of PhDs that have been awarded, lots of papers that are in the combining of two different types of methodologies, two different data sets, into a coherent, more comprehensive picture image of the subsurface. And so I want to jump into the combination of Richard's equation and direct current resistivity. And so this is in the context of vadose zone flow and a geophysical method. So bringing in that context that I was talking about before. So to combine these two methods, if you have that pond and there's sand underneath there and you are raining on the top of it, so you're changing the boundary condition at sort of the top of your model, and that's through time. And so you have some infiltration front coming down through the subsurface, and how and where that goes is dependent on the hydraulic properties. And so hydraulic conductivity sort of is showing where that goes. On the geophysics side of things, what we're imaging is electrical conductivity. And so that's the physical property that direct current resistivity is sensitive to. You hook a battery up to the ground, you measure a lot of potential differences, and you can reconstruct using inverse theory a model, an image of electrical conductivity, and that is varying through time. And so if we jump back to Richard's equation, or this infiltration front, a wet sand is much more electrically conductive than a dry sand. And so there's a empirical relationship between these two models. And so the changing in time can be mapped through some sort of empirical relationship, maybe Archie's equation, to a changing electrical conductivity model. So this is sort of the conceptual integration of this hydrogeophysics discipline. And so the Ford model, starting with hydraulic properties, simulating using Richard's equation, mapping using some empirical relation down to a geophysical model, and then creating data. And so that's the Ford sense. What we're interested in the hydrogeophysics side of things is the inverse side of that. And so you're starting with potential differences and propagating that all the way through each of these things so that you're actually interested in the hydrologic model. And so in this case, although the output of most geophysics side of things is this conductivity estimate everywhere, we're actually interested in the hydrogeology side of things in the hydrologic estimate. And what's interesting about the combination of these two disciplines is that we've sort of vastly opened up the amount of data that we can collect. We can collect a lot of direct current resistivity data. We can't necessarily collect a lot of saturation data or pressure head data, at least not in a dense sense. You can potentially do it in a sparse sense, so at a single borehole through time, but you don't have sort of a dense estimate of data. So that changes sort of what you might expect to be able to get about your hydrogeologic model. So I want to jump into Richard's equation a little bit. And Richard's equation is the partial differential equation that describes vadose zone flow. And so it's time stepping in this water content side of things, which is a nonlinear function of the pressure head. And then you have some diffusion side of things. Again, you have a nonlinear relationship in here, and you have some infection due to gravity. And so that's the partial differential equation that describes that. Before I said that the hydraulic property was primarily sort of hydraulic conductivity, but in the vadose zone, hydraulic conductivity is actually a function of pressure head, and there's another function in there, which is water content, which is either a function of pressure head, or there's quite a few empirical relations that describe how these different physical properties interact. And so we have these curves which describe that in there. And so this is a nonlinear differential equation, so we need to solve it with the appropriate numerical methods. But in the inverse side of things, again, this is going from something that we know to describing this infiltration front through time. But we don't actually know what these curves are. And so if we sort of look into how those are described in the literature, that again is an empirical relation with maybe 5 parameters that we want to estimate everywhere in space. And those parameters might be heterogeneous, they might be anisotropic, and so it's a difficult inverse problem to attack. So just looking at the literature, and this is in the context of sort of the hydrogeology side of things, not the hydrogeophysics side of things, what people are typically doing is laboratory estimates where they have very controlled small samples, and they're trying to estimate these parameters of those, because that again allows you to simulate in the Ford sense. And so there's been a lot of work done on sort of that small inverse modeling side of things, and then on the sort of large hydrologic modeling side of things. So if you have an entire groundwater basin, again, the data that you collect is going to be sparse, potentially in time and in space. And so even though you're maybe simulating a large model, what you're actually estimated, or what you're interested in the parameter estimation side of things, is actually a small inverse model. And so how people are, sort of the state of the science is to use either Bayesian techniques or perturbation techniques using something like PEST to estimate those small models. But in the context of sort of this going from that sparse data estimate to a dense, or sorry, the sparse data, which is like a very good estimate, to a dense estimate of data. Again, we don't actually have all of the saturation or water content side of things. We have an estimate of it through some empirical mapping. That becomes sort of a big inverse problem. And so the models that we're interested in are much bigger. And so in the 2016 review paper, it sort of like the state of the science, this either a probabilistic treatment or using this perturbation, finite difference side of things outside of the model, means that that's actually computationally infeasible for most three-dimensional applications. The scale that we're interested in for coupling this to geophysics. And so this is sort of a problem to go to the three-dimensional side of things. And so this is sort of the first thing that I attacked in my thesis. So I'm just going to very quickly go through some of the numerical methods. We're using finite volume in space. We're being fully implicit in time, discretizing that in space and then in time. And that nonlinearity due to the Van Genuchten curves, those empirical relations, is through an iterative solve, either a Picard or a Newton method. On the sensitivity side of things, and this is really where the sort of the crux of the problem is, it requires formulation of Richard's equation as this block linear system through time. And there's some intricacies there due to the nonlinearity and also model dependence in sort of any part of that chain of how the two methods are connected. And another piece is if we actually solve this, so if we take the inverse of that in some way and apply it to the right-hand side, this is your sensitivity matrix here, and that's a large, dense matrix. And so if we actually hold that all in memory, that's maybe too much for what we can handle on a machine. And so we want to be able to access that sensitivity through matrix vector products. So a brief example of this is sort of if we're thinking about the context of that pond, the managed aquifer recharge, and we have some block of sediment here with two different types of materials, sand, loamy sand, then we can infiltrate from the top. And if we're collecting those water content estimates, we can hopefully estimate the hydraulic properties. And so on the inverse side of things, in this example, I've only estimated for a single hydraulic property. There are sort of 5 distributed in space at each point in this model. I've inverted for the hydraulic conductivity, which has been done before in the literature. What hasn't been done, I don't think ever before, is a 3-dimensional inversion for distributed hydraulic conductivity. And so this is probably the largest inversion for Richard's equation. Yeah, which is cool. So, and one of the reasons that has been done, or hasn't been done, is because the context of the problem has changed. Because we're going from that sparse data estimate to a dense model estimate everywhere, we can expect more from our inverse problems. And so this, the dense sensitivity matrix in this case has 500 million elements. If we're going to use something like PEST, which is a finite difference external method, that would take a very long time to actually compute the sensitivity. In this method, you can do it on sort of a single laptop in a matter of hours. And even if you were to do it with that external method, if you're not doing it implicitly, you're going to have problems in terms of memory. And so going down by sort of a factor of 100 if you use this methodology. Cool. So that was one of the things that I tackled in my thesis, was the scalability of Richard's equation in the context of direct current resistivity inversions. So if we go back to the context of where we're looking, we have a whole bunch of questions. So now it might be possible to map these two together, because this is at sort of the same model scale that we're expecting from the data. But there are a massive amount of questions along the way about how to actually tie these things together. And those are sort of by their nature interdisciplinary questions. So one of the papers that I read early on was talking about these problems, and they showed that the coupling of these two methods had sort of these direct advantages, but it forced the hydrogeologist and the geophysicist to formulate a consistent framework. And that had like all sorts of advantages, but it was also, because of sort of its difficulty, it's the primary limit to routine implementation of these style of inversions. And if it's the primary limit, then we can't actually ask lots of questions. It can ask maybe one question, spend a year implementing it, and move on. And so that's sort of the style of things that has been happening in the literature. And so my research has been sort of into this framework idea that might lower the barrier to entry to address the primary limit to this problem. And so if we look back at the discipline, before I was saying that if you combine any two of these methods, there's a PhD sort of at the end of it. And so there are these PhD-sized barriers between the geophysical methods, and there are large barriers between going outside of our field as well. And so you might not actually be able to implement or solve the scientific question that you're after. And so it's motivating the need for sort of a consistent framework so that you can take any two data types, combine it into a consistent model of the subsurface, and expose that through an interface to external use. So a computational science framework lays out a set of standards that allows multiple researchers to write units of software, these components, in this case, geophysical inversions, with the confidence that those components work with other components in that same framework. And so it's a systematic approach to that interdisciplinary problem. In our case, we need to be able to simulate physics, compute sensitivities efficiently, regularize and optimize, and that's a lot of the research that's done in this discipline. We also need to be able to capture inversion heuristics and couple and join them in some way. And so the questions are, what are those components? And what are the interfaces of those components? And we know a lot about that in the discipline of geophysics. And so what I've sort of been doing is studying that such that it can be exposed externally to our discipline, and also potentially, if you're organizing these things appropriately, that can allow you to ask new questions inside your discipline as well. And so this is the framework that I'm proposing, and I'm just going to walk through it very briefly to give you a flavor of it. You need to be able to discretize your problem in some way. I'm using a lot of finite volume techniques and aligning those meshes to interfaces, or refining to areas of interest. Once you have that, you need to be able to simulate physics. So there are differential operators on those meshes, which you can combine in a sensible way to simulate physics, to go from the equations to the code to the physics in a smooth way. And then you need to forward simulate. So this is going from your model, going to your physical properties, your physics, your fields, your sources, and your receivers. And the way that this is laid out is that these are all sort of combinatorial, so that you can go from one, switch it out, have another one, if that makes sense for the problem. On the inverse side of things, there's a lot of work in our discipline about data misfits, different types of regularizations, and being able to combine those in a sensible way. And in a sensible way sort of means is the difference between optimization and the inversion discipline. And so there's all sorts of workflows that are created in the literature that are specific to geophysics and hydrogeophysics, which need to reach into every single component in this to actually make it work. And so what this is sort of under the hood is a whole lot of lines of code that have been written, but they're just not just like put down. It's the process of creating structure from that. And so thinking about the interfaces and the sensible components that are appropriate for this discipline. And so there's a lot of structure and organization and thought that's gone into this. So this framework we've published in a couple places. One about the geophysical inversion methodology, sort of at a general side of things, but talking about sort of those components and those interfaces and how they fit together. And then about the forward simulation framework in the context of electromagnetics. And we've also sort of been doing a lot of case studies, so proving to ourselves that this framework is appropriate to the various case studies that we have in front of us. So that's, I had a couple SVG abstracts about imaging hydraulic fracturing using a joint inversion, imaging seawater intrusions with electromagnetics, and modeling electromagnetics in the presence of cased wells. And so this is demonstrating sort of the utility of the framework, and again, sort of proving that to ourselves. But in some sense, you need to, like, the point of a framework is that it allows multiple scientists to work together and provide those standards such that they can. And so there's some groundwork to do to get there, and that's really in the implementation side of things, and doing that sort of like exposing that in an appropriate way. And so that means having software testing and documentation and sort of all of the engineering aspects. But the point of that is that we can have a conversation as a discipline about these things. And so we started that conversation. We hosted an international workshop that we started talking about that standards and making sure that it is appropriate for the discipline. And that's, yeah, the components and interfaces that people can use to solve their own problems. And that has started to be happening. And so that the software framework was published in 2015. And there's a whole bunch of work that's taking those and building upon it. And really having other scientists, so not the original authors, have their own ideas about how to combine these things. And that's sort of the power of the research that has gone into this. So in summary, the two sort of contributions of this work are this computationally scalable in the context of Richard's equation and direct current resistivity, and putting those together in a way that attacks this 3D application. And then the second side of things was trying to attack this primary limit to the routine implementation of integrated geoscience inversions. And how to do that is to look out to the interdisciplinary community and ask how they build these things. And that is through the definitions of frameworks and the standards of the components and the interfaces. And one of the things that this author said, who was the Darcy lecturer in 2016, is that requires an uncommon level of collaboration during scientific analysis. And what a framework hopefully addresses is that that becomes much more common because the future geoscience problems are bigger than any one domain. So thank you very much.